Hello, welcome back to this class, and we are talking about the determination of Ka values and what we are talking in terms of the corresponding concentrations. So, if we have a concentration like C powered C multiplied by D powered D, the number of moles. So, how we quantitatively determine the concentrations of the different species present over there. So, this we have seen that is A powered A and B powered B. So, what are the species you can have in a particular reaction like this? So, that we will see that if we have a reaction like this, where we can have the species H A, the species H B and H A minus and B. So, all of them, that means concentration of these two, and so we have 5 species together. So, their individual concentrations are therefore important to determine the corresponding Ka value. So, if we have simple acetic acid dissociation, we know that this is a weak acid, and this dissociation is very important because we will be talking something related to not only the dissociation of acid, but also the corresponding fate of the corresponding anion which is produced in the reaction, because since this is a weak acid, dissociation is not much, K value is less. So, if this particular acid is weak, its conjugate base will be strong enough. So, how this particular anion can function and can control the corresponding equilibrium. So, what we see that the number of moles, because this C, D, A and B. So, we are talking, and the powered thing for the corresponding concentration, we are powered by the corresponding strength. So, if we consider that how far this equilibrium is going from left to right, if it is weak, that equilibrium lies far to the left. So, equilibrium is only going towards the left. So, this will be a long arrow, the other one is a very strong short arrow. So, it is going to the left, and the concentration what we are talking or we are thinking about is the number of moles of this acid, that means the H A. If we consider that this is your H A, so the number of moles of this H A. So, what is there, this H A dissolved per liter of the solution, number is dissolved per liter of the solution. So, we will get at some point that the CHA, which is nothing but your analytical concentration, which we are interested to determine. So, this analytical concentration, that how we determine this particular one. So, this one compared to your hydrochloric acid, as I told you in our previous class, which is completely dissociated. So, if you have HCl, so this HCl can give rise to your H plus Cl minus, and this is going more on the right hand side. So, it is staying or lies far to the right. This particular equilibrium is staying on the left, and this particular equilibrium is going to the right. So, the concentration of the individual species involved in a particular equilibrium process or equilibrium reaction is different. So, that way what we get this particular reaction, that means the same Ka value, the Ka value for the species A, B, C, D, what we are discussing so far in this particular concentration for the acid. So, the acid dissociation constant, A stands for acid, is for the corresponding H plus concentration, corresponding acetate ion concentration, and the concentration of the undissociated acetic acid. So, all will be there, and this particular value is less, basically is 1.76 into 10 to the power minus 5 molar. So, this particular one, if we consider, that also give rise to how we determine or how we record or how we tabulate or represent the value in terms of this pK value like that of your pH. So, its pK value is 4.75. So, this is an interesting parameter for acetic acid, giving a value of 4.75. So, which is related to the corresponding acid dissociation constant of your acetic acid. So, experimentally we can determine also for this particular parameter for some other species, where we find that this particular species can be useful to determine or label a particular compound, organic compound, which can be again a weak acid like that of our acetic acid. So, we will see that some point of time we will again bring this thing. That means, there are several acid base indicators we all know, like that of our phenolphthalein, that of our methyl orange, and also the methyl red. So, if they are like acetic acid, a weak acid, weak organic acid, so you can determine the corresponding pK value for these, and which is basically labeled, which is a characteristic property for all these indicators, where we all know that pK for these, and we will also see why this particular pK is so important, because these pK values will be directly related to the corresponding color change range for all these indicators. Okay. So, what we see therefore, that how this particular pK value is important, and if we consider the corresponding dissociation, if we try to plot the corresponding dissociation of these, that means how far the equilibrium is lying towards the left or towards the right. So, if we plot the fraction of the corresponding acid, the fraction of the corresponding HA in ionized form, with respect to that of our concentration in moles per liter. So, we have defined and we have considered two such acids. So, if we can have this particular acid for this reaction, so if we have this is 0.5, then we have 0.75, then we have 1, and this is 0.25, starting the value at 0, and this vertical line is also at the midpoint, giving 0.05 molar concentration and 0.1 molar, because in most of the cases we are handling a decimolar solution, that means the final concentration is 0.1 molar solution we are talking about. So, for this particular case, that means when we have the hydrochloric acid, so if we have hydrochloric acid, so when we have hydrochloric acid, the corresponding curve for this fraction of this dissociation can be like this. So, you see that at a very low concentration, when concentration is approaching 0, you have almost 100% dissociation. So, this fraction is almost 1. So, this is for the corresponding dissociation of HCl. So, at the lower concentration range, this particular range, your hydrochloric acid is fully dissociated. But what about this corresponding acetic acid? Acetic acid, by definition we all know that this is the corresponding weak acid. So, it is going like this, and this is your acetic acid. So, extent of dissociation thus in this particular case is dependent strongly on the concentration, it is dependent on the concentration. So, this dissociation, so it is going say to up to 0.25 and above 0.25 fraction is said therefore 25%. So, we see 25% dissociation of acetic acid only at the lower range. So, up to this range only, otherwise it is decreasing towards the higher concentration range. So, this particular range of this concentration is therefore important. So, the magnitude of dissociation, that means which particular strength or which particular concentration we are handling for this particular titration or any other reaction, where we see that a particular dissociation of HOAC between H plus and acetate ion, and if we consider that the fraction of the dissociation, we all know that the fraction of this dissociation is x. So, x H plus and x acetate ion is also forming, and if we have the original analytical concentration of acetic acid is basically CHOAC is the original acid strength or the concentration which is present before dissociation. So, after dissociation it is C minus x. So, as we define Ka, so Ka will be x square, this multiplication of these two x, and C of HOAC minus x is equal to nothing but your x square minus 0.1 minus x, because we have taken and we are considering the corresponding high acetic acid in this particular range of concentration. So, how this dissociation and all these things can be there? If the dissociation is very less, if the magnitude of x is very small, it can be ignored and this can be equivalent to CHOAC, the original acid concentration what we are considering. So, this way how we can find out the corresponding concentration of H plus which is produced in the reaction medium. That means, in a 0.1 molar acetic acid solution, if we have, this is the acid. So, if we have a 0.1 molar acetic acid solution, we should be able to tell about the corresponding H plus which is coming out, the amount of H plus which is coming out from HOAC, considering the corresponding Ka value, the dissociation constant value we all know. So, it will be 1.34 into 10 to the power minus 3 molar concentration. So, we can have some good idea about the concentration of all these acids, what is forming at that particular point. So, this guidance for this particular concentration is very important, very much important in terms of the corresponding equilibrium process, because we will be seeing that this particular thermodynamic quantity what we are handling for these analytical processes is the corresponding identification of any of these species, either this acid we will be considering for your acid based titrations or the something which will be related or tagged to the corresponding acetate ion form. So, that we just slowly considering for the equilibrium constant. So far we have seen that corresponding species how we know, but the equilibrium constant what we are talking about is the corresponding thermodynamic parameter, but it has no relationship to the rate of the reaction, because the rate of the reaction what we are talking in terms of the corresponding titration reaction. Titration is also a reaction where the analyte is getting titrated by the reagent. So, if the reaction is very fast enough, we have to have some procedure where very quickly we can determine the product of that particular analytical reaction. So, that is independent of that of your K value or the corresponding equilibrium constant. So, like that of our example, this is a typical textbook table which has been taken from your Skoog's book. So, this how we can write down basically, and what we are seeing so far, that the corresponding reaction, that means the dissociation of acetic acid, which has been abbreviated as HOAC so far. So, that dissociation we are basically considering for a type of equilibrium which is known as the dissociation of a weak acid or a weak base. So, these two reactions, these two equilibrium reactions are nothing but the corresponding reactions involving their constants for the dissociation reaction. So, this is basically the corresponding reaction where one is Ka, another is Kb. So, in case of that Ka reaction, what we see that K is equal to, in place of H plus we will be writing as the corresponding hydronium ion, because in presence of water the proton forming from this acetic acid is forming H3O plus. So, these two concentrations divided by the acetic acid concentration will give you the corresponding Ka value. Similarly, for Kb, what we see that this is your conjugate base. Acetate ion is your conjugate base which is reacting with water. So, base will accept the corresponding proton, and this base will accept the proton forming hydroxide ion and the acetic acid. So, Kb will be written in this particular fashion, but this particular Kb also you can be able to write if we have ammonia plus H3O plus or H plus forming ammonium ion and the corresponding water molecule. So, that also give rise to the corresponding Kb value. So, any equilibrium related to some reaction, that means dissociation of acid or some association with proton or the dissociation in terms of the reaction of the water with the corresponding base, will give rise to this K, the equilibrium constant for acid, and Kb is the equilibrium constant for the base. So, these things we can apply very quickly for other chemical equilibrium. So, the importance of the analytical chemistry is that how we can follow the different equilibrium. It is not only the acid base equilibrium, but we are following this which is a very basic reaction or a very simple reaction what we can follow, and we can have so many applications for that, so many calculations from your school days you have studied the determination of the pH of the medium and how much concentration you are getting for a particular strong acid or a strong base or a weak acid or a weak base. So, very first thing we can also figure out from the determination of K and Kb values is the involvement of the Kw, which is a very important parameter which we consider as the dissociation of water. Because water in water, that means your solvent is water and water molecules are present, some amount of dissociation can take place. That is why we have a pH scale of 0 to 14, where we see that the corresponding range or corresponding thing has been standardized with respect to the corresponding reaction of H2O forming H3O plus and HO minus, and Kw will be nothing but your product of the concentration of H3O plus and HO minus. Then the same thing can be applied to some solubility product constant which is Ksp, and where we have a sparingly soluble substance and its ion in a saturated solution. So, the formation of barium sulphate, as we know all that this barium sulphate is a very important reaction what we can study in terms of the corresponding qualitative identification of sulphate ion. So, if we have SO4 2 minus ion and we want to identify this we all know that is a very simple reaction we follow. We add a solution of barium chloride to an unknown solution of sulphate ion. Say the solution has been prepared from sodium sulphate. So, this will give rise to the formation of barium sulphate, and visually within a test tube we detect basically by our naked eyes through its formation of a white precipitate. So, if the addition of barium chloride to any solution which is a clear solution, because this is a sodium solution, say sodium plus, which is a clear colorless solution, clear colorless solution, and this is giving you a white precipitate. So, definitely this reaction what is forming over there is nothing but we have SO4 2 minus, the analyte, which we are trying to detect by a qualitative test. By the addition of a reagent, and we are only focused our attention to the cation, because we are trying to identify the anion. So, barium we are giving that barium as a barium chloride, which is soluble in water. So, this giving rise to the precipitate as barium sulphate, and we write this as the corresponding precipitate, white precipitate of barium sulphate. So, what we see that this particular one, so it is a solid and which is sparingly soluble. So, think that this is an equilibrium process and is going from left to right. It does not mean that you have 100% of this barium sulphate is forming from the reaction medium. So, still you have some barium plus 2 plus and SO4 2 minus in the medium, that we all know that the precipitating reaction is also controlled by the corresponding solubility product constant or Ksp value. So, if we know the Ksp value, so the Ksp value if it is very high or if it is low, we know that what concentration of barium can be added to get the corresponding precipitate of barium sulphate. That means, the individual concentration of this barium and the sulphates are important. So, if we know the Ksp value, then the product of these two concentrations should exceed the Ksp value of the barium sulphate. If it exceeds the Ksp value, the product of these two, then only you get the barium sulphate precipitation. Otherwise, you have this barium and the sulphate ion in the solution, and this solid what we are getting when we are trying to write is that a corresponding solution which is sparingly soluble. That means, some amount of solubility is definitely there, and it can provide barium ion and the sulphate ion in the solution medium. So, we have this Ksp value which is the solubility product K value for this equilibrium of the formation of a sparingly soluble solid, which is largely very less soluble in the medium, and Ksp value will be the product of the individual concentrations of the barium 2 plus and sulphate 2 minus. Then we can have a very important thing, that means the considering the corresponding beta values, the formation constants, how we can follow analytically a particular metal complex reaction. We consider at the corresponding complexation reaction. It is a different type of reaction, is not that the corresponding salt formation, that means the nickel cyanide is not forming. That means NiCN2, the charge balance or the charge neutralization reaction can give rise to NiCN2 only, but this is a complexation reaction where we find that cyanides are your ligands and not two cyanides are very useful, such that it is required for charge neutralization, but you require 4. That means, on the left hand side you have cation and anion, but on the right hand side also a anionic metal complex is forming, and if it is coming from sodium cyanide you get the corresponding sodium salt. If it is coming from potassium salt, you will be getting the corresponding potassium salt of this, and like that of all other equilibrium constant value, it is written and its definition is different. That means, it is abbreviated as beta, not K. So, beta for beta 4 we are writing. That means, it is involving 4 steps, 4 equilibrium steps it is involving. So, 1, 2, 3, 4. So, you will have beta 1, beta 2, beta 3 and beta 4, that we will find out afterwards also for any other examples where we can identify that no, this is not a simple acid base type of reaction, it is definitely acid base reaction, because we all know that this cation, which is very much similar to your acid. So, this is the acidic site and these ligands are the bases, corresponding bases. So, this is again another form of acid base reaction, but giving rise to the corresponding complexation reaction. And the beta is therefore, we are determining, that means the overall formation constant for this tetracyanonickelate complex. Okay. Then if we go for the redox reaction, where not the proton transfer is taking place, but the electron transfer can take place, where the permanganate ion is reduced to manganese ion of Mn2 plus by ferrous ion. So, ferrous will be oxidized to ferric ion and permanganate is reduced to Mn2 plus, and we find that the K redox value. So, this particular one is also very much important, because this K redox, this corresponding value, K value for this equilibrium constant is very much important for their individual species which is present, and how easily you can detect that this particular reaction is going only in presence of some amount of acid. So, it is in the acid medium, some concentration of acid is required, and we can find out the corresponding redox potential value. That means, the driving force for that particular reaction for the individual couple, that means the ferric ferrous couple and the permanganate manganese couple, we all know, and how it is going from left to right. The K value we all know, and from the K value we can find out the corresponding free energy change and the corresponding values or the matching values for the delta G0 values, and from there we can find out the E0 values from there. So, from these redox things, all these things are theoretically very much essential to know. So, you should again go back to your theory classes for the redox reactions before we can handle, we can go for the corresponding identification, because from this particular reaction what we can see that you can immediately identify the species. This is your A species, this is your B species. So, we can identify the nature of the permanganate ion, the nature of the ferrous ion, nature of the manganese ion and the nature of the ferric ion, or we can quantitatively determine the amount of unknown ferrous ion present in the medium by titrating it with a solution, standard solution of potassium permanganate. Okay. And lastly, another thing is very much important, where we can consider a particular species, particular chemical species which is getting distributed between two medium which is immiscible, such as organic and aqueous medium. If it is therefore the iodine, and iodine we all know that is soluble in water medium as well as it is soluble in the aqueous medium, and what should be the distribution. So, that is known as the distribution equilibrium for a solute between immiscible solvents. So, water and any other solvent like chloroform or dichloromethane or benzene, they are immiscible with that of our water, and we can have some distribution between these. And again, these two species in two medium basically. So, we should be able to consider the corresponding concentration of iodine in organic medium and corresponding concentration of iodine in aqueous medium, and that will tell us the corresponding value of Kd, because if we know the individual concentrations in the organic phase and the individual concentration in the aqueous phase, this has tremendous application in all other cases, some catalytic reactions where we consider the phase transfer catalysts. So, which particular phase we will be utilizing, that is very important to tell that how we can consider that particular phase such that you do the reaction in some other phase, and if the active ingredient such as iodine is also there, can be used there, which can be transferred from one particular phase to the other phase. So, these things, and also we will be talking in terms of the corresponding salt which is sparingly soluble. Just now I told you that the precipitation of barium sulphate, and when it is forming that particular salt, if we take and if we dissolve it in water, we find that some amount of these ions are coming out from that particular salt, and this is considered as the corresponding sparingly soluble salt. A very small amount is available in the solution, and we can be able to detect that particular ion or the cation or the anion in that particular solution, because you have certain amount of solubility in that particular medium. So, that we will just discuss and we will see in detail afterwards, that if we have some amount of excess barium iodide which is equilibrated with water. So, what we will consider this as the corresponding salt which is giving us some amount of barium concentration, some amount of iodide concentration. So, which is nothing but your reverse of your barium sulphate formation. That barium sulphate is forming as a precipitate, some amount of barium plus is still there along with the sulphate. But in the same way, if we take barium iodide and if we the solid iodide is try to dissolve it to water. So, equilibrium, how quickly the equilibrium is reached due to the dissolution of that particular barium iodide. So, that we will discuss in detail, because we are slowly moving towards the corresponding reaction of the hydrolysis of some salt, that means the salt hydrolysis. So, how sparingly soluble salts are utilized, that we will see for during the hydrolysis of the salt also. Thank you very much.